So let me start with the definition of an invariant random subgroup. And at first time, when you see this definition, it looks very unnatural. But then I'll explain why it is natural and why people care about them. And then we will talk about some results about acylindrically hyperbolic groups. So what is an invariant random subgroup? So the common abbreviation is IRS, which all Americans love. So because this is the agency which collects taxes in the States. So for me, all the groups are going to be countable in this talk. So whenever I say a group, what I mean is a countable group. And I'll just omit the word countable. So G is a group. And let me just say it once, countable. And by S of G, I denote the space of all subgroups of G, which you may think as a subset of the space of all subsets of G, or in other words, you can think of it as 0, 1 to the power G, the set of all subsets. And this set has natural topology. It's Tikhonov topology here, which makes it a compact space. So this space inherits this topology, and if G is countable, then it's compact space. So let me explain maybe what it means for a sequence of subgroups to converge to some limit. So a sequence of subgroups Hi converges to subgroup H in this space if and only if for every finite subset F of the group G, there exists n natural number such that for all lowercase n bigger than or equal is capital N, we have Hi intersects F equals the intersection of H and F. So in other words, oh, right, let's put I here. It's Hi here. So in other words, if you look at finite subsets, or in case of finitely generated groups, you can think of finite balls, then this system, this sequence stabilizes inside this finite subset. It eventually stabilizes. That's what it means for a sequence of subgroups to converge to a limit. So S of G is compact with respect to this topology. It's an exercise. And of course, the group G acts on the space of subgroups. And the action is by conjugation. So the action of an element G in a group G, the image of a subgroup H under this action is just G inverse HG.
So Dennis, can I just ask, when you defined S of G, you said subsets, but now you keep saying subgroups.
No, I said subgroups.
Subgroups,
But this is a subset of the set of subsets, right? And the topology defined here, it's actually the restriction of the Tikhonov topology on this space. The action is by conjugation. And an invariant random subgroup is just a G-invariant probability measure, let's say Borel probability measure on this compact space. So, well, what G invariant means is clear. It's invariant under the action of G. So G acts by measure-preserving transformations. Borel is the standard term. Probability measure means that the measure of the whole set S of G is 1. So it's a finite Borel measure, and moreover, we normalize it. Well, maybe I will start with a couple of examples. The first example, every normal subgroup, you can think of normal subgroups as particular cases of invariant random subgroups. So let's take first example, N, which is a normal subgroup of any group G, and then define for any subset of S of G, define the measure of A to be 1 if N is contained in A and 0 otherwise. Now, this is clearly a Borel measure, right? It's an atomic measure. It's a probability measure, and it is G invariant because N is normal. So if A contains N, then every conjugate copy of A is going to contain A, right? Because N is normal. So that's important here. So this is first example. Now, the second example actually explains why such a strange object is interesting. So the second example is due to George Mackey. And he considered this example well before the term geometric group theory was born. So the example is this. So let's assume that our group G acts by measure-preserving transformations on a Borel space. Let's say mu is a Borel probability measure. So my abbreviation for this will be PMP, which means probability measure-preserving action. So X is a Borel space with probability measure. This is a probability measure. This is a measure-preserving action. So first, let me introduce some standard notation. So let's denote by G sub X, where X is a point in this space X, the stabilizer of this point. So this is the set of all G in G, such that Gx equals X. That's the stabilizer of my point. So Now you have a map from X to S of G such that a point, little x, of this space is mapped to the stabilizer of the point. Okay? Now you can use this map to define a probability measure here. So what you do is the following. So you define a measure, let's call it nu, on S of G by the rule nu of A, where A is a subset of S of G, equals mu, where mu is the measure on our space X, of F inverse of A. So, well, first of all, and this is the most essential thing in this example, this measure is well defined. In general, this trick doesn't work. So as everybody knows, for this trick to work, what you need F to be a Borel map, or measurable function, whatever you call it. And the fact that this map is Borel, it's not very difficult. So for countable groups, it's maybe like 5 lines proof. But it was first noticed in this paper by Maki in more general settings of locally compact topological groups, locally compact second countable topological groups, but I don't want to talk about that. So anyway, this map is Borel, and therefore the trick works. Now, why is it why is this measure G invariant? So it's G invariant because what is the conjugate, G, let's say G sub X, G inverse? Well, if you take a stabilizer conjugated this way, what you get is a stabilizer of Gx, right? And from here, you can easily see that nu is G invariant. That's because mu was G invariant. So conjugation on this space corresponds to shifts by elements of G, or images under action of elements of G, on the original space X. And since this measure was G invariant, remember it's measure preserving action, this measure is going to be G invariant, conjugacy invariant. So that's the second main example. And moreover, it's a theorem of Miklos Albert. Who else was there? I think Glasner and Vira, which says that for every group G, and for every invariant random subgroup mu of G. So here it's a slight abuse of language because I say invariant random subgroup of G, but what I really mean is a measure on the set of all subgroups. So it's nothing inside G, it's some measure, right? But still, so for every invariant random subgroup of G, there exists a probability measure preserving action of this group on some Borel space. Maybe I'll put nu here, just for my notation to agree with the previous notation, and mu here, such that nu and mu are related by this formula. Let's call it star. So in other words, if you take these two results together, what you see that invariant random subgroups of my group G are in one-to-one correspondence with probability measure preserving actions of G. So in some sense, if you want to study probability measure preserving actions of G, or just classical dynamical systems for an arbitrary group G, it's the same as studying invariant random subgroups. And that's the main motivation. So the term invariant random subgroup is due to Abert, Glasner, and Virac. Here, you don't care. But in their case, it will be compact.
And mu is only finitely additive?
No, it's Borel measure.
So it's like sigma.
It's Borel measure, yeah. That's countably additive. Okay. Now I have to figure out how to work with these blackboards. Let's try this. Good. So now before
I don't see how you can get this for the example of the zero.
right, because if you take the natural action, then you'll get the normalizer. Well, you have to take the Bernoulli shift on the quotient group. Think about it. You take Bernoulli shift on the quotient group, and that's it. So it's not immediately trivial. So the theorem is easy, but not trivial. So before proceeding to some results about invariant random subgroups, I have to introduce some standard language. So I will say that, and it's sort of standard thing, we say that an invariant random subgroup mu of G has some property P if, where P is just some property, if H has this property for mu almost every H in G. So for example, I say that my invariant random subgroup is finite if almost every subgroup of G is finite. So remember, mu is a measure on the set of all subgroups. So it does make sense to say that mu almost every subgroup of G has some property, which means that the measure of the set of subgroups with this property is 1. And that's the standard language. So it's interesting that sometimes, or I would rather say in many situations, you have some sort of rigidity for invariant random subgroups. And here the story begins with a result of Stuck and Zimmer from 1994, who proved the following. They proved that every let's say ergodic probability measure preserving action, and just to remind you, an action is ergodic, a measure preserving action of a group is ergodic if every invariant subset either has measure 0 or measure 1. So in other words, there are no non-trivial invariant subsets, right? And we will also say that an IRS mu of G is ergodic if for every G invariant subset A of G, mu of A is either 0 or 1, if this measure is ergodic. So Stuck and Zimmer proved that every ergodic probability measure preserving action of S, L, N, Z, where N is at least 3, and essentially SLNZ is my abbreviation for an irreducible lattice in a semi-simple Lie group where every simple factor has rank at least 2. Okay? But that's an example. So it's sort of particular case of the theorem is either, let's say, has either finite stabilizers or finite orbits, which is a very strong result. And we can reformulate it in terms of invariant random subgroups. So in the modern language, it says that every invariant random subgroup of S, L, and Z is finite or of finite index. So that's one result which I wanted to mention. And on the other hand, if you go to groups like free groups, which are very far from these lattices, then you see lots of invariant random subgroups. So there is another theorem by Lewis Bowen, which says that F2, free group with on 2 generators, as well as Fn for every n, at least 2, has uncountably many, in fact continuously many, 2 to the aleph 0, non-atomic ergodic invariant random subgroups. So if you have an invariant random subgroup which is simultaneously non-atomic and ergodic, it cannot come from the first example there, so it cannot come from a normal subgroup, so you really have to construct something else. Of course, free groups, they have uncountably many normal subgroups, so there are already uncountably many invariant random subgroups, but if you in addition require them to be non-atomic and ergodic, so that example is atomic, but then you can cheat a little bit. For example, you can take 2 normal subgroups and define a measure by saying that this normal subgroup has weight 1/2 and this normal subgroup has weight 1/2, but that's not ergodic because you have 2 invariant subsets of measure 1/2. Yes, ergodic, right, thanks.
What's an example of an ergodic IRS where it's actually finite?
Where is what?
Every subgroup, almost every subgroup is finite.
The trivial one? Well, any central subgroup gives you, so this example is ergodic. It's just atomic, right? So this is an ergodic example.
Yeah, but here, not every, you're saying that in this case, almost every subgroup is finite?
No, not almost every subgroup is finite, but if n is finite, then it is. Obviously, it's exercise. No, well, No, there is no classification. I mean, there are examples, but there is no classification. So if you think what's the difference between F2 and SLNZ, then you see that this is the group which has some sort of hyperbolic properties, and SLNZ, if n is at least 3, is very far from being hyperbolic in any sense. So what you can expect is that if you have a group which acts nicely on a hyperbolic space, then you probably have 2 to the aleph 0 invariant random subgroups which are non-atomic and ergodic. If you don't want them to be non-atomic and ergodic, then you can just use normal subgroups, and you know that in many cases, if you have a group which acts nicely on a hyperbolic space, it has uncountably many normal subgroups. So one example, but you have to be a little bit careful, because there is this theorem of Jesse Peterson and Andreas Thom, which says that every invariant random subgroup of, so again I'm stating just a particular case, PSL2 Q over rationals is either trivial or the whole group. So, of course, everybody knows PSL2 over an infinite field. So it's simple, but so it doesn't have any normal subgroups except the trivial ones, but it doesn't have invariant random subgroups either, which is sort of surprising because this group acts non-elementarily on the hyperbolic plane. Just use the embedding of this group to PSL2C. So you have to be careful. It's not true that if you have a group which acts non-elementarily on a hyperbolic space, then the group has uncountably many non-atomic ergodic invariant random subgroups. And this is the point where acylindrically hyperbolic groups come into play. So let me remind you the definition. We say that the action okay, maybe I'll just save my time and cheat as well. So I'll just say that a group is called acylindrically hyperbolic if it admits a non-elementary acylindrical action on a hyperbolic space. And again, instead of explaining the terms here, I will rather provide you with some examples of acylindrically hyperbolic groups. I mean, the definition itself is sort of useless, because to derive something from the very definition, you have to become familiar with some tricks, how to use this acylindricity of the action and so on. But so here are some examples. So first of all, this is a generalization of hyperbolic groups. So every non-elementary hyperbolic group or even relatively hyperbolic group is acylindrically hyperbolic. Second, the classical example is mapping class groups, let's say of closed surfaces where G is at least 1. They're acylindrically hyperbolic as well. So for those who know what acylindricity of the action means, so how you prove that this group is acylindrically hyperbolic, it acts acylindrically on the curve complex, which is hyperbolic due to the result of Mazur and Minsky, and the action is acylindrical due to the auto-automorphism group of Fn, where n is at least 2. So the fact that this group admits an acylindrical action on a hyperbolic space, non-elementary acylindrical action on a hyperbolic space, is a combination of several results. A result of Bestvina and Handel, and then my result joined with Vincent Girardel and François Damany, and then another result from my paper about acylindrically hyperbolic groups where the term was suggested. So anyway, I don't want to put all the names here. Let's say most three-manifold groups, that's what already was mentioned. So let me say that, okay, let's just say it this way. So if you think about closed irreducible manifolds, then there is some sort of trichotomy for the fundamental group. Either the fundamental group is virtually solvable, in which case the manifold is fairly small, or the manifold is Seifert-Fibert, in which case the fundamental group is not acylindrically hyperbolic, that's provable, or the fundamental group is acylindrically hyperbolic. So if you rule out some small manifolds, like Seifert-Fibert and those with virtually solvable fundamental groups, then all others have acylindrically hyperbolic fundamental groups. And there are many other examples. Well, maybe I'll mention just one, number 5. Finitely presented groups with, let's say, residually finite, finitely presented residually finite groups with the first L2 Betti number positive. So this, for example, implies that every group of deficiency, well, not quite this result implies that, but a little bit more general result implies. So groups of deficiency at least 2 are acylindrically hyperbolic. So a group has deficiency at least 2 if it's finitely presented and has a finite presentation where the number of generators is 2 plus the number of relations. For one-relator groups, which have deficiency 2 if they have at least 3 generators. So for one-relator groups, this was proved in my joint paper with Ashot Minassian, and for groups of deficiency 2, it was proved in my paper about groups of this sort. So anyway, so there are lots of examples. And now there is a theorem by Grigorchuk. I should start with Bowen. Grigorchuk and Kravchenko who proved that every acylindrically hyperbolic group, so AH, my abbreviation for acylindrically hyperbolic, has uncountably many non-atomic, ergodic, invariant random subgroups. They didn't state the theorem in this form. So unfortunately, they only stated the theorem for non-elementary hyperbolic groups and mapping class groups for some reason, and out of n. But the proof they give essentially works for all acylindrically hyperbolic groups, because the idea of the proof is based on 2 facts. The first fact is that if you take F infinity, free group on infinitely many generators, then it has 2 to the aleph 0 non-atomic ergodic, so I'll just put dots here, non-atomic ergodic invariant random subgroups which are invariant under all automorphisms. So the so-called characteristic invariant random subgroups. That's the first fact, which the proof of this is based on a generalization of this theorem by Bowen. And the second fact which they use is due to François Damany, Vincent Girardel, and myself, is that if G is acylindrically hyperbolic, then there exists a subgroup isomorphic to F infinity, which is normal in G. So from this fact and this fact, you can construct uncountably many invariant random subgroups on G that will be supported on subgroups of F infinity, and the fact that they are automorphically invariant characteristic allows you to extend them to G invariant random subgroups in this situation. Okay, so now if you compare this result to the result of Stuck and Zimmer, you think, well, is there any rigidity for acylindrically hyperbolic groups? Probably not, because there are uncountably many invariant random subgroups here. And that's the question I was interested in. But nevertheless, it turns out that there is some sort of rigidity. There is some sort of dichotomy for invariant random subgroups of acylindrically hyperbolic groups. And to state this result, I'll need one more definition. So let's say that G is an acylindrically hyperbolic group. And we say that a subgroup H in G is geometrically dense if for every acylindrical action of G on a hyperbolic space S, the limit set of G is the same as the limit set of H. So what it means that from the point of view of acylindrical actions on hyperbolic space, if you look at H sort of asymptotically, it's indistinguishable from G. So just by looking at the boundary of your hyperbolic space, you cannot distinguish H from G. So here are some examples. First, every infinite normal subgroup of G is geometrically dense, which is not so difficult, sort of easy. So normal subgroups are geometrically dense. And second example, which gives you examples of big subgroups which are not geometrically dense, a quasi-convex subgroup H of a hyperbolic group is geometrically dense, let me abbreviate it as GD, if and only if it is of finite index. So of course, if you have a subgroup of finite index, it's geometrically dense. But if H is also quasi-convex and the group G is hyperbolic, if H has infinite index, it's still huge subgroup, but it's not geometrically dense, and that's also well known. So now I'm ready to state the main result, which I wanted to talk about. And the motivation for this result was that when I looked at the proof of this theorem by Bowen, Grigorchuk, and Kravchenko, I noticed that the subgroups which they construct here, these invariant random subgroups, they are very close, in some sense, to subgroups coming from this example 1.